Welcome back! Today we're going to be working on dilations and similarity day number 3, content objective. The students will be able to perform a dilation given a scale factor and center of dilation. Language objective, students will be able to explain verbally how to dilate figures using coordinate plane. Why am I learning this? Well, it's important for real-world problems like creating video games. So we've done this before where we went ahead and found congruent angles, congruent sides. So just a quick reminder of how we do that. We go ahead and match corresponding points to find the corresponding angles, and then we match corresponding sides together to find which sides are congruent. So rigid motion always leads to congruent figures. Rigid motion, just a quick reminder, will include translation, reflections, and rotations. Congruent, the symbol we use looks like this, and basically congruent means same shape and same size. When we have a congruent shape, we're going to see that all corresponding angles are congruent and all corresponding sides are congruent. And this here is considered our congruent statement. This tells us a lot because it can tell us which angles are congruent, which side lengths are congruent. By having this congruent statement, it does, once again, tell us a lot of information. Then we want to go ahead and discuss that two figures are congruent if you can manage to get the other shape by using either a rigid motion or a sequence of rigid motion. So basically, if you can move one of the figures using one of the transformation or a series of them, then you know for sure that they are congruent because these types of transformations does preserve congruency. Dilation leads to something else. It actually leads to a similar figure, which is slightly different. So similar, the symbol we use for that looks something like this. So it looks like the approximation symbol with only one squiggle, I guess you can say. So similar means it's the same shape. Okay, so here you'll notice they're exactly the same shape. Okay, and more so, we can prove that they are similar by showing that the sides are proportional to one another. So here is your similarity statement. It looks it's close to how you would write a congruent statement, except you use, of course, the similar symbol instead of the congruent symbol. Angles are still congruent with a dilation, okay? Because with angles, they're not affected when the sizes change, okay? So the angles continue to be congruent. Now, the sides are not necessarily congruent. They are proportional. Okay, so proportional, so let's go ahead and take a look here. If I wanted to compare, first of all, I want to note that the shape, the size of the triangle is decreasing. So I would expect my quote-unquote scale factor to be less than 1. So I'm going to set it up that way. So here, for example, if I were to compare a line segment AB, I'm going to put it as a denominator. Why? Because I expect the fraction to be less than 1. So the way to do that is to keep 8 as a denominator and go ahead and put LM of 4 as my numerator. So that would give me 4/8. So notice that if I reverse that, I would have 8 over 4, which would make me believe that if I were to think of this in terms of scale factor, that it would be a 2, which could be misleading. Now, when we're talking about just ratios in general, it does not matter the order, but just to remind you, if we were talking about scale factor, it does matter, okay? A number less than 1 means that the shape decreased in size, and a scale factor greater than 1 means the shape increased, and a scale factor of 1 means the shape didn't change at all. So let's take a look at a couple more. So here I can go ahead and take a look at segment BC. So line segment BC corresponds to line segment LN. So I'm going to put LN on top and go ahead and put that this is 3 over 6. And last but not least, I can go ahead and say that segment AC corresponds to segment MN. So there I can say the fraction would be set up as 5 over 10. And you'll see with all of these, they do reduce down to 1/2. So this would be my scale factor. Okay, so once again, when I'm just talking about a ratio in general, it doesn't matter which way, okay, unless you are specifically told from large to smaller, small to large. It could be considered 1/2 or 2, but specifically when we're talking about scale factor, you do need to make sure it's written in a particular order to show what's happening to the size of the pre-image to the image. So again, since it decreased in size, it would be 1/2 and not 2/1, which is 2, because that would make me believe that the shape increased instead. Just a quick reminder, the variable we use for scale factor is r, so I could also write it as r equals 1/2. So two figures are said to be similar if there is a sequence of rigid motion and dilation that take one figure onto the other, or it could just be one dilation. So number 1, it says a dilation with the center of dilation at the origin maps triangle ABC to triangle A prime, B prime, C prime. So this is what we have. If AB equals 3 and A prime, B prime equals 6, what is the scale factor of the dilation? Well, let's see. It went from AB of 3 to A prime, B prime to 6. So obviously the side length increased. So I expect my scale factor to be greater than 1. Now, by what factor was it increasing by? Well, it went from a 3 to a 6. It doubled in size. And for that reason, I can go ahead and state the scale factor was 2 because it was doubled. 3 times 2 is what gives me 6. So the sides of the new triangle are twice as big as the original. Now, B prime C prime is 8. What is the length of BC? So now they're giving us the length after the dilation. Okay, so which means if it's dilated to give me an 8, and the scale factor is 2, that means something times 2 gave me 8. So I'm going to say the length is 4. Now, a very common mistake that I anticipate some of my students to do is they might accidentally do 2 times 8 and say, oh, it's 16. But remember, the pre-image was smaller than the image. So here, the length of the pre-image should be shorter than the length of the image. Okay, so now, length AC equals 5. So just a quick reminder, this is my pre-image. This is the length of the pre-image. What is the length of A prime, C prime? So here, since this is after the dilation, I do expect this length to be larger. How many times larger? 2 times, because that is my scale factor. So I expect the length of A prime, C prime to be doubled. So doubled, 5 doubled is going to give me 10. Now, the next question is, if the slope of segment AB is 0, what's the slope of segment A prime, B prime? Well, the slope does not change with dilations, with translations, reflections, or rotations. It does not change no matter which type of transformation we use. So if the slope was 0, it's going to remain 0. So corresponding line segments have the same exact slope. And you're going to find this to be true across the 4 different transformations we've learned so far: dilation, translation, reflections, and rotations. So E, if the slope of segment A prime C prime is 4/3, what's the slope of segment AC? Again, the slope never changes no matter what the 4 different transformations that we use. So if it was originally 4/3 for A prime, if the new slope of the image is A prime, for A prime C prime is 4/3, then the slope of the original line segment was originally 4/3 as well. So what is the coordinate rule? Well, first starting off with x comma y, we know that whatever happens to the x happens to the y, and generally it's changed by a factor of the scale factor. So here we're going to do double the x as well as double the y. So it looks something like that. Okay, so now moving on. Here it says number 2, triangle ABC has been dilated to obtain triangle A prime, B prime, C prime about the origin. Write a similarity statement. So first it's good to understand which vertices corresponds to which. So obviously I think from here, because they were nicely labeled from A to A prime, we can go ahead and say that A corresponds to A prime, B corresponds to B prime, and C corresponds to C prime. And for those reasons, I'm just going to go ahead and write something. First, naming the first triangle, I'm just going to call it ABC. But similar, remember, we're using a different symbol. This is congruent, but the annotation for similarity looks like this. So it's basically this top squiggle without the equal sign beneath it. So now I'm going to put triangle. Well, A corresponds to A prime, so I'm going to go ahead and put A prime. B corresponds to B prime, and C corresponds to C prime. So that would be my similarity statement. So it's very close to a congruent statement, except you don't have the equal sign underneath it. Next, it says, triangle ABC has been dilated to obtain triangle A prime, B prime, C prime about the origin. List the corresponding angles. So all I need to do now is state which angle corresponds to which angle. Well, I'm going to go ahead and say that angle A corresponds to A prime. And for those reasons, they're also congruent. So let's go ahead and go back and annotate it instead. Let's say angle A is congruent to A prime. So one tick mark there. Let's see, what else? Angle B corresponds to angle B prime. So those are congruent. And angle C corresponds to angle C prime. So I'm going to go ahead and write that those are congruent. Okay, so no matter what type of transformation we're looking at, whether it's translation, reflection, rotations, or dilations, you're going to find that the angles will always be congruent from pre-image to image. So if I asked you this, if angle C prime is 38 degrees, so that's this angle right here, if this is 38 degrees, then what is the angle measurement for angle C? Well, since they're congruent, I would say that angle C is also 38 degrees. So to answer the question, I'm going to say the measure of angle C is 38 degrees as well. Because we know that corresponding angles are congruent. And again, this goes for all of the 4 transformations we've learned this far. Next, it says, show that the corresponding sides are proportional. How do I do that? First, it's going to be the easiest to find corresponding sides that are either vertical or horizontal, because it's just a matter of counting the number of units to figure out the length. So here I'm going to start with the length from A prime to B prime. This is, let me just highlight so you can easily see which line I'm referring to. This is 1, 2, 3, 4 units long. So I'm going to go ahead and put 4. And then line segment AB, well, that is 1, 2 units tall. So I'm going to go ahead and put 2. So 4 divided by 2 is 2. Now I'm going to continue this on with some more corresponding lengths. Starting with B prime, C prime. Let's go ahead and count how long this length is. So it's 1, 2, 3, 4, 5, 6. So this has a length of 6, and the length of BC has a length of 1, 2, 3. So 6 divided by 3 is also 2. Okay, so far so good. Since they are wanting us to prove that they are proportional, I do need to show that all of them have a ratio of 2. So I need to do the last line segment. So now I'm going to have to find the length of A prime, C prime, as well as AC. So first, starting with this, I can't just count, of course. So I'm going to have to apply the Pythagorean theorem to find this missing length. So in order to do that, I need to figure out how long this leg is. It's 1, 2, 3, 4 units tall. And then it's 1, 2, 3, 4, 5, 6 units wide. So in order to find this missing length, I'm going to first understand that this is the hypotenuse. I'm just going to call it C. For some, I'll be honest, this might be a little confusing because C is used as a point and C prime is used. So to make things a little bit more clear, why don't we use E instead? Okay, so now let's go ahead and put 4 squared plus 6 squared equals E squared. we're going to have 16 plus 36 equals e squared. And then we're going to have 52 equals e squared. Take the square root of both sides. And I'm going to be left with e equals the square root of 52. So that is the length of this here. Now what I'm going to have to do is find the length of AC. So I'm going to repeat the process, but I'm going to go ahead and find the length of this line segment here. I'm going to still use the Pythagorean theorem because it is a right triangle, as I can see here. The length here, the length of this leg is 2. The length of this leg is 3. So applying the Pythagorean theorem to find this missing length, I'm just going to go ahead and call it f. I'll put 2 squared plus 3 squared equals f squared. 4 plus 9 equals f squared. 13 equals f squared. Take the square root of both sides, and I'm going to come to the conclusion that f here is the square root of 13. So now what we're going to want to do is check, okay, well, can I reduce this? A good idea would be to check to see if you can divide both sides by the smaller number, which is 13. And guess what? I think it does go in evenly 4 times. Let's just double check. Yes, it does. So you could divide both by the square root of 13. And you'd be left with the square root of 4 over 13 divided, square root of 13 divided by square root of 13 is 1. Here, square root of 4 is 2, so I'm going to be left with 2 over 1, which is just 2. Here's proof that they are proportional, okay? So there you go. There's proof right there that the corresponding sides are proportional. So corresponding sides are proportional, and the way you prove it is by showing that the ratios are equivalent. Next, find the scale factor. So here, to make things a little bit easier, in order to find the scale factor, you can just use what you did earlier. Use the fact that we know that the lengths are proportional. And by what? Well, first understand that the shape was increasing in size. Okay, so you can go ahead and compare, well, this length is 2 and this length is 4. By what factor is it increasing? Well, it's increasing by a factor of 2. So in order to do that, you could have set up here B prime A prime over BA, which would have given you 4 over 2. Or maybe you wanted to go a different route and say, let's look at BC and B prime C prime. Well, BC is 3. B prime C prime is 1, 2, 3, 4, 5, 6. So from the pre-image to image, how did 3 become 6? Well, once again, it was doubling. But if you want to set it up as a ratio, you can go ahead and put B prime C prime over BC. So B prime C prime is 6 and BC is 3, which gives you 2. Okay, so there's multiple ways of getting the scale factor. So the sides of the new triangle are twice as big as the original. For example, this length was 2, it doubled to 4 after the dilation. BC was 3, after the dilation it doubled to 6. Number 3, ABCD has been dilated to obtain triangle. This is not a triangle, this is incorrect. So let's put A prime, B prime, C prime, D prime about the origin. Write a similarity statement. First, it's a similarity statement because it's a dilation. We wouldn't put congruent because obviously they're not the same shape. They're not the same size, correction. So here I'm going to go ahead and write, okay, well, first of all, A corresponds to A prime, D corresponds to D prime, C corresponds to C prime, and B corresponds to B prime. So for that reason, if I choose to write, I don't know, quad ABCD, I'm going to say that's similar to quad A prime, B prime, C prime, D prime. Because once again, you want to make sure they correspond to the correct vertex. Let's clean that up there. Okay, next, what is the scale factor? Well, in order to find the scale factor, all you really need to do is compare two corresponding line segments. Okay, it's a good idea to first start with, okay, did the shape increase or did it decrease? Well, if it went from A, B, C, D to A prime, B prime, C prime, D prime, I'm going to definitely say the scale factor should be less than 1. Okay, if it's greater than 1, then that would be very misleading because the shape was reduced. So what you always want to do is set up, okay, let's say I want to use line segments AD and A prime, D prime. Those are the line segments I want my focus to be on. Okay, the most crucial part is setting it up correctly. There's two ways that someone might set it up, but there's only one way that would lead you to the correct scale factor. So I will show you both, and I want you to decide what would be better. So here, you could set it up as A prime, D prime over AD, or you might set it up as AD over A prime, D prime. Again, there's only one way to set it up correctly. Let's figure out which method that would be. So let's see, A prime, D prime, that length is 1, 2. AD would be 1, 2, 3, 4, 5, 6, 7, 8. So here, if I set it up, my scale factor would be 1/4. If I set it up this way, it would be the reciprocal, so AD was 8, and A prime, D prime is 2, which reduces to 4. So which one looks correct? Is it 1/4 or is it 4? Well, let's recall this shape was reduced in size. And because it's reduced in size, I expect my scale factor to be less than 1. Now, only one of these numbers is less than 1. So which method should you use? Option A or option B? Hopefully your answer is option A. My biggest concern is a lot of students might have the idea of which corresponding lengths corresponds to what, but they might set it up incorrectly. So it's very important that you do take a step back, look at the image, and see what's happening. Is it increasing or is it decreasing? And make sure your scale factor matches that image. So for this reason, I'm going to go ahead and say the scale factor is 1/4. And just a quick reminder, we can use R to represent the scale factor. So the sides of the new quadrilateral are 1/4 as big as the original. So here, let me ask you real quick. If I said angle B is 107 degrees, what is the angle of B prime? The answer is 107 as well. Because again, with congruent and with similar shapes, angles are always congruent. Corresponding angles are always congruent. Next, number 4, element O is graphed on the grid below. Dilate element O by a factor of 1/2 with the center of dilation at the origin. Label the new quadrilateral L prime, M prime, N prime, O prime. So first what I'm going to do is put my center of dilation at the origin. And then I'm just going to go ahead and look at how far I'd have to move to each vertex. So for L, I have to go up 1, 2, 3, 4, and then to the left 1, 2. So let's just do a quick recap. 4 up, and then 2 to the left. Since they're wanting us to change it by a scale factor of 1/2, I'm going to have to take half of the distance here. So instead of moving 4, I'm going to go move 2 up, and instead of moving 2 to the left, I'm only going to move 1 to the left. So I'm going to go ahead and go up 2 and 1 to the left, and here is my L prime. I'm going to repeat this process. For example, for M, I have to go up 1, 2, 3, 4. So for M, I have to go 4 up, and then I have to go 1, 2, 3, 4 to the right. Since I am scaling it down to 1/2, I'm no longer going 4, I'm going to only go 2, because 1/2 of 4 is 2. And instead of going 4 to the right, I'm only going to go 2 to the right. So starting at the origin, because that's the center of dilation, I'm going to go 2 up and then 2 to the right. And there is M prime. Going to repeat this for S. Okay, so for S, I had to, well, just kidding, not S. Saw that 5 for a second, thought it was an S. Let's go to N. So for n, I'm just having to move 1, 2, 3, 4 to the left. So I'm just going to cut this in half and only go 2 to the left. So here we're going to go 1, 2, and here is n prime. And then last but not least, for O, we had to move 1, 2, 3, 4 down. 4 down. And then from there, we had to go 2 to the left. So 2 to the left. So now we're just going to do half of that, which means you're only going to go 2 down. And instead of going 2 to the left, you're only going to go 1 to the left because that's half. So from the origin, we're going to go 2 down and then 1 to the left. And we're going to go ahead and call that O prime. And there you have your new image. So notice we went ahead and called it L prime, M prime, N prime, O prime. Next question is now asking us to translate what we just created, L prime, M prime, N prime, O prime, according to the rule x comma y gives you x minus 6, y plus 2. And label the new shape L prime, L double prime, M double prime, N double prime, O double prime. First, let's understand x minus 6 means to move it. X-axis moves from left to right. So this means we're going to move it to the left 6 units. So let's do that. We're going to take this and move it 6 units to the left. Okay, so if you didn't see, it moved from L prime to L double prime here. 1, 2, 3, 4, 5, 6. Okay, now we're going to go ahead and interpret y plus 2 as being, okay, well, y is the motion of up or down. Since it's a positive 2, that means it's going to go up 2 units. So from here, we're going to go up 2 units, and there is our new location. So that's it for part B. For part C, it says write a statement that shows a relationship between LMNO and L prime, M prime, N prime, O prime. Well, from LMNO to L prime, M prime, N prime, O prime, I would consider these shapes to be similar because one is a dilation of the other. So again, we're going to use this symbol here to indicate that they are similar. Next question. Why? Again, because the two shapes, one was a dilation of the other, so they are similar. Part D, write a statement that shows a relationship between L prime, M prime, N prime, O prime, and L double prime, M double prime, N double prime, O double prime. Well, let's see. First of all, we can definitely see that the shapes are congruent. So I'm going to go ahead and write that the shapes are congruent. But there's something else. They are also considered to be similar. Why? Well, let's remember, you can have a scale factor of 1. And if you do have a scale factor of 1, then you know that the shapes are exactly the same. So guess what? All congruent shapes are also considered to be similar. Why? Because they could be in terms of a dilation with a scale factor of 1. Because again, a dilation with a scale factor of 1 doesn't change the size at all. Okay. Number 5, the triangle below are similar. List a sequence of transformation that verifies that the similarities of the two figures. So first of all, there are multiple answers to get from one triangle to the other to prove that they are similar. Okay, I'm just going to go ahead and give you the answer that I used to figure out how one shape got to the other. Now you may have a different answer that can also be correct, so please keep that in mind. There is more than one answer. So the first thing that I see is LMN is being rotated 90 degrees clockwise to give me this here. Okay, now from here to create this larger right triangle, I notice it's being scaled by a factor of 2. Now how can I prove it? Well, let's see. First, to get to this point, it's going up 2 and to the right 1. Okay, so up 2 and to the right 1. So in order to get here, notice I'm having to move 1, 2, 3, 4, and then to the right 2. So up 4, and then to the right 2. Notice, by what factor is 1 turning to 2 and 2 turning into 4? It's moving by a factor of 2. So here, let's just verify and make sure. Here, we would have to go to the right 3 and then up 2. So the right 3 and then up 2. Forgive my sloppy handwriting. Let's see. According to what I just said, I'm thinking that the scale factor is 2. Let me see. If I double this, that would mean I would have to go to the right 6 and then up 4. Let's see if that happens. To the right 6. 1, 2, 3, 4, 5, 6, and then up 4. 1, 2, 3, 4. Perfect. And last but not least, I would want to check the same for these 2 points here that are corresponding to one another. Here it's going up 1 and then 1, 2, 3, 4, 5, 6. So up 1 and then to the, sorry, not up 1, right 1 and then up 6. So to double this, that would mean I would have to go to the right 2 and then up 12. So let's see. To the right 2 and then up 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There you go. So I've come to the conclusion that first it's rotated 90 degrees clockwise, and then from there it's being dilated by a scale factor of 2. And this dilation occurred around the origin. That was the center of dilation. So now it's asking me to write a similarity statement for the triangles. Again, it's very important that you make sure the corresponding vertices are matching up as you write your similarity statement. So I'm going to go ahead and match them up real quick. I'm going to say L corresponds to S, M corresponds to T, and N corresponds to R. And for those reasons, I can go ahead and put triangle LMN is similar to triangle. Okay, so here, what corresponds to L? L corresponds to S, so I'm going to put S. What corresponds to M? M corresponds to T. And then what corresponds to N? Well, N corresponds to R. So here is my similarity statement. Now, could you have written something slightly different but still be correct? Absolutely. The order of the very first one doesn't really matter. However, the order of the second one does. As long as L corresponds to S, M corresponds to T, and N corresponds to R, you are correct. Okay, so now here, the quadrilateral below are similar. List a sequence of transformation that verifies the similarity of the two figures. So first, I'm just going to go ahead and state what I see. The first thing I see is this quadrilateral here is being reflected off of the y-axis to give me something like that. Now from here, I can see that the shape is definitely too large, so it needs to be dilated. So by what factor though? Well, let's see. Originally, we're going up 2 to the right 2, but I only want to go up 1 to the right 1. So notice I'm going to have to decrease the movement by half. So for those reasons, I'm going to go ahead and say I'm going to scale it by a scale factor of 1/2. So what's one possible answer? Well, I can say that it was reflected off of the y-axis, and then it was followed by a dilation around the center of the origin by a scale factor of 1/2. So write a similarity statement. So again, it's important for you to go ahead and find which one corresponds to which. So I'm going to say T corresponds to Z, S corresponds to W, or R corresponds to X, and U corresponds to Y. So here I can write quad, any order for the first one, doesn't matter. R, S, T, U is similar to quad. Well, let's see. R corresponds to X, S corresponds to W, T corresponds to Z, and then U corresponds to Y. So there is my statement. So here, the triangle below are similar. Prove it. So I don't think I've been stressing this enough, so I do want to mention the way that I'm proving that they are similar is by showing that there's a sequence of transformations that include dilation. Dilation is what creates the similar figures, so as long as I'm showing that there's a series of transformations that include dilation, then I know for sure that these shapes are similar. So for this particular transformation, I noticed first that it's being reflected, particularly off of this line here, which we would call, it's going through the y-axis, so this is y equals -3. So it's being reflected off of the equation y equals -3. Now from here, I'm noticing, okay, from the origin, we're going up 2, but we need to go up 6. So if I'm right now going only up 2, but I need to go up all the way to 6, it's being tripled. But let me check. Okay, here, from the origin, I'd have to go down 1, to the left 2. So if I triple this, that would mean I'd have to go down 3 and 6 to the right. Does that agree? Yes. So for those reasons, I can go ahead and state that it is a reflection across the line y equals -3, followed by a dilation with the center at 0, 0, and a scale factor of 3 because it tripled in size. Like so. So to write a similarity statement, again, you just need to find corresponding vertices. So C corresponds to S. This would have been C prime, this would have been A prime, and this would have been B prime. So this one's slightly trickier. So you want to make sure here B corresponds to T and A corresponds to U. So notice A corresponds to U, B corresponds to T, and C corresponds to S. This could have been written in a different order, such as BAC is similar to triangle, but this time you would have to write it as TUS. So again, there's multiple ways to write the similarity statement. Okay, just know that there is a wrong way as well, so not everything is correct. Next. Now, one thing that I did want to talk about this one, because it is a little bit tricky, is that you have to be very careful. Some students may just say, okay, well, it's reflected here. And then I want to go ahead and triple the size. Okay, well, if your center of dilation is at the origin, you'll see here at this vertex, it is 0 away. So even if I triple this, it will still remain here. You would have to go 1, 2, 3 down and 2 to the left. So in that case, you would have to triple it. Instead of going 3 down, you have to go 9. So 3, 6, 9. And instead of going 2 to the left, you would have to go 6 because that's tripled. So 2, 4, 6. And you would repeat that on the other side. And you'd find that the triangle would end up down here. So please don't assume that you can dilate it at any number and it would give it to the exact spot that you'd want. You actually need to check, okay? So now it says, determine whether the figures below are congruent, similar, or neither. Provide a justification for your answer. Well, first of all, I can prove that they are similar if I can manage to show there's a sequence of transformations that include dilation. So the first thing I am going to recognize is, hey, it's a 180-degree rotation. From there, it looks like the length here was 4 and then it went to 8. So automatically I'm thinking it's definitely doubled. But let's clarify here. The height is 4 and then it increased to a height of 8. So I'm definitely going to say that it increased by a scale factor of 2 because it doubled in size. So for this reason, I'm going to go ahead and say that these two figures are similar. The smaller triangle can be mapped to the larger one by doing a 180-degree rotation followed by a dilation with the center at the origin and a scale factor of 2. Next, determine whether the figures below are congruent, similar, or neither. Provide a justification for your answer. So right away, I'm noticing a reflection across the y-axis to give me this. And then from there, it's definitely getting larger, so I'm going to pick a scale factor greater than 1. Well, let's see. from the origin, I'm going to pick this point to focus on first. It's going up 4 to the left 2. Okay, now to get to this point, I'm going to have to go up 8 to the left 4. So originally, we only went up 4, but the next one we went up 8. So it doubled. So let's see if that works. Okay, here, let's test it out. We're going up 2 and then to the left 3. So if I double this, I would have to go up 4 to the left 6. 2, 4, 6. Perfect. So far, so good. Next, here, we're having to move up 4 to the left 4. So if I double this, we're going to have to go up 8 to the right 8. So far, so good. Last but not least, we're going to have to go up 2 to the left 5. So to double this, I'm going to have to go up 4 to the left 10. And there you have it. So I'm going to say from there, not only did we reflect off of the y-axis, we're going to have to dilate it by a scale factor of 2, where the center of dilation is at the origin. Okay, so these figures are definitely similar because we had to use a dilation in the sequence. So now it says here, determine whether the following transformation or sequence of transformations will result in similar figures, congruent figures, or neither. Provide a justification for your answer. First one, here it says, we're going to do x minus 6, y plus 2. First of all, I recognize that this is a translation, and you know that all translations will result in a congruent figures because it is a rigid motion. So I'm going to go ahead and say that they're congruent. But you notice here that I also included similar. Why? Because once again, with similar figures are created from dilations. Couldn't it be possible to have a dilation with a scale factor of 1? Absolutely. With a scale factor of 1, the shapes are exactly the same. They are congruent. So all similar shapes are considered all congruent shapes are considered to be similar. Basically, a scale factor of 1. B, here we have 2x, so double the x, double the y. This is definitely a dilation, and for those reasons, I'm going to say that they will be similar. This one here, 2x comma 3y, this one, first of all, is not a dilation. Remember, whatever happens to x needs to happen to y. And so for this reason, it's not a dilation. It's definitely not a reflection, a rotation, or a translation. So I'm going to say it's neither. Here, x plus 5 comma y plus 5 followed by a 90-degree rotation counterclockwise about the origin. So this may seem a little intense, but let's take it one at a time. Here is a translation. For sure, I know the two shapes are congruent. Now from there, we went ahead and rotated it 90 degrees counterclockwise. Well, guess what? Even after a rotation, the shapes are still congruent because both of these transformations are rigid motions. So for those reasons, I'm going to go ahead and say that the shapes are congruent. But remember, congruent shapes are also considered similar. It's basically a dilation with a scale factor of 1. This one here, it looks like a dilation because we're taking 1/4 of x and 1/4 of y, followed by this here, which doesn't look like one that we're familiar with where y and x is flipped. But understanding alone that this is a dilation, I know already that the shapes are going to be similar. Last but not least, here we have x comma y plus 4. This is a translation, followed by a rotation. Again, both of these are a rigid motion, and for those reasons, I know that the shapes are going to be congruent. And yet again, we know congruent shapes are also similar. So I'm going to go ahead and say that this one is congruent and similar. So that is going to conclude the lesson for today. Thank you so much for tuning into this very long lesson. And like always, until next time, bye.